guys, welcome to another video in the series of coding. Today we are going to do the problem which is called number of excellent pairs. A pair of numbers is called excellent if the following conditions are satisfied. Both the numbers exist in the array and the sum of the number of set bits in num1 or num2 and num1 and num2 is greater than or equal to k. Let's try to understand what they are saying with some example. Let's say this is the given array with the given numbers 5, 1, 3, 6, 5, 3. Let's say we are given k in the input as 4. So first of all I have converted this to binary representation so that it is easier for us to understand. For example, the binary representation of 5 is 101, the binary representation of 1 is 1, the binary representation of 3 is 1, and so on. Okay, so now we have to find out how many excellent pairs are there in the array. Now what is an excellent pair? Excellent pair is first of all a pair consisting of two numbers when if you take the OR of these two numbers and you take the AND of these two numbers, you will get some output. If you count the number of set bits in both of them, it will be greater than equal to k. Now let's try to take some examples so that we can understand this easily. Okay, let's say that our first number is 5, okay, and the second number is 6. So what is the binary representation of 5? It is 101, right? So 5 corresponds to 101 and 6 corresponds to 110. Okay, so let's perform the two operations. Let's take the OR of these two numbers 101 and 110. What is the OR? If you write the output of the OR, it is going to be 111, right? And you take the AND of these two numbers. What is the AND of these two numbers? If you write the output by performing the AND operation, it's going to be 100. Now you have to count the number of set bits in both of this. So let's count the set bits. So when you perform the OR operation, the number of set bits is 3, right? And when you perform the AND operation, the number of set bits is 1. So what is 3 plus 1? 3 plus 1 is equal to 4, right? So the final answer is 4. Now you have to check whether 4 is greater than equal to k or not. So in our example, we have taken k equal to 4, right? So we have to check if 4 is greater than equal to 4 or not. So this is true because of this 5-6 pair, right? The pair 5-6 is an excellent pair, okay? And like this you have to count all such excellent pairs and you have to return the total as the answer. Okay, now how can we solve this problem? So the brute force way to solve this problem is to list down all such pairs and then perform the OR and the AND operation and then count the number of set bits in both of them and check whether that is greater than equal to k or not. So to list all the pairs, the time complexity is going to be order of n square. So let's see if we can optimize this. So let's try to understand what we are doing in the OR and the AND operation and let's see how we can optimize. So let's take example of two numbers to understand. We have number 1. I have written the binary representation of number 1 and I have written the binary representation of number 2 because we are only concerned with the OR and the AND operation. So first of all, let me write what is going to be the output of the OR operation, right? So 1 or 0 is going to be 1, 0 or 1 is going to be 1, and so on, right? So let me just write the final output. So we know that the OR operation is going to give this as the output. Now let me write the output of the AND operation. So when you perform the AND operation on these two numbers, for example 1 and 0, here you will get a 0, 0 and 1, here you will get a 0, and so on, right? So let me write the output of the AND operation. So it is going to be this, right? So now you have to count the total number of set bits in both the OR and the AND outputs, right? So for example, in the OR output, let us see what are the set bits 1, 2, 3, 4, 5, 6. Now let's see the set bits in the AND output 1, 2. So you have 2 set bits. Now 6 plus 2 is equal to 8. So we are only concerned with 8 as our answer. Okay, so this is what we are supposed to find out finally, 8. Okay, now how are we getting the total number of set bits as 8? Let's see. How are we going to get a set bit in the OR? You need to have a 1 in any of the numbers, right? Then only you will get a 1 because of the OR operator, right? And let's consider the set bit for AND operator. So you need to have a 1 in both of the numbers, then only you will get a set bit in the AND output, right? So this is the logic. Now let's see how we can get this answer 8. Finally we need to get 8 set bits, right? Can we get this answer 8 without even performing the operations? Let's see how we can do that. Okay, let's just see the number 1, right? So let me erase all this. Let's start from the first number. Let's see the number 1. We have in the number 1, we see that this bit is set, right? You see that this bit is having a value of 1, means it is set. So now we are sure that if we perform the OR operation, at least we will get a 1 in the output, because if you have a 1, you have any 1, right? In the OR you will definitely get a 1 as the output, right? Because 1 will ensure that you get 1 in the output also. So if you perform the OR operation, you know you will get a 1, but this 1 can also contribute to the AND, right? Because of this 1, when will you get a 1 in the AND? If this number had also been 1, right? If both of them had been 1, then you would have got 1 in the AND output also. So you are not sure about the AND output, but definitely you know that this 1 will at least contribute a set bit in the OR operation, okay? So let's continue with understanding this. So because of this 1, you know that corresponding to this one you will get a 1 in the OR output. Now let's see this one corresponding to this one, also you know at least for sure because of this one in the OR of the output you will get a 1. Let's consider this one. Because of this one you know that you will get a 1 in the OR output. Now let's see this one. Because of this one also at least you will get a 1 in the OR output, okay? Now let's see this one in number 2. Now let's come to number 2. You are seeing this one. Now this one will contribute to a 1 in the OR output, okay? Now let's consider this one, okay? Now it gets interesting. Let's see this one. This one, we cannot say that this one will contribute 1 to the OR output. It will, but this one is not going to bring a additional set bit in the OR output, because already corresponding to this one, right, corresponding to this bit, in this bit already, because of the previous 1 in number 1, you have already considered that the output is having a 1, right? You have already counted it. So now when you are counting this one, you can see that because of this one you will get a 1 in the AND output, because if you are already seeing a repeated one, if you are seeing a 1 at the same bit which is also present in number 1 and in number 2, if you are seeing a 1 which is present at the same position as it was present in number 1 also, if you are seeing a repeated one, that means that 1 and 1 will give a AND output of 1, right? So this 1 which is getting repeated is going to contribute to a set bit in the AND output, okay? Very important. Now let's continue. Let's think about the next one, okay? Let's think about this one. This one is going to contribute a 1 to the OR output, because it's for the first time at this bit position. For the very first time at this bit position you are seeing a 1, so this one is going to contribute to the OR output, right? This one is going to cause a 1 in the OR output, okay? It's not going to cause a 1 in the this one is not going to give a 1 in the AND output, because this one is not repeated in this bit position. This one is occurring for the very first time, right? The other bit in number 1 is 0, right? So 0 or 1 is going to give you 1 in the OR output, but 0 and 1 is going to give you a 0. So what I mean to say is that when you are counting this one which is a 1 for the first time at this bit position, this is contributing a 1 in the OR output, but if you are seeing a repeated one, it is going to contribute in the AND output, okay? So because of this one I can count a 1 in the OR output, okay? Now let me continue. Now I am seeing a 1 that is repeated again, okay? Now this one was already occurring in number 1, now again at the same bit position it's occurring in number 2. That means that this one is going to contribute a 1 in the AND output, okay? So now what we did, we counted the total number of bits in number 1 and in number 2. Corresponding to some ones we are getting output in the OR, corresponding to some ones we are getting output in the AND, but all the ones are contributing either in the OR output or in the AND output. So what does this mean? So you have to just count the total number of ones in both the numbers and that will give you the same answer, okay? So let's see this example. What are the total number of set bits in the OR output? It is 6, right? It is coming from these 6 ones, 1, 2, 3, 4, 5, 6, right? It is coming from these 6 ones. And consider the number of set bits in the AND output. It is 2. It is coming from these 2 ones, right? So what is the total number of ones in both number 1 and number 2? Number 1 has 4 ones, number 2 has 4 ones. 4 plus 4 is equal to 8, right? So 6 plus 2 is also equal to 8. So instead of even performing the OR and the AND operation, we need not even perform these operations. You can just count the total number of set bits in number 1 and number 2, and if you just add them, you will still get the same answer, okay? So this is the entire logic. Let's take a very simple example again to understand this. let me just quickly take one example. Let's say we have a num1 and let's say you have a num2. Okay, let's say that the number is 10110, and let's say the number 2 is 01011. Okay, something like this, just taking a random example. Now without even performing the OR and the AND operation, I can just tell you, like if you perform the OR and the AND operation and you count the total number of bits, what is going to be the total number of answer? How we can tell that? It's just going to be the same as the total number of bits in both the numbers. So what is the bit in first number? 3. What is the number of bits in the second number? 6, right? So 3 again. So 3 plus 3 is equal to 6. So the total number of final bits will be equal to 6 only. Okay, now let's check if what we claimed was true. Let's just perform the OR and the AND operation. So if we perform the OR operation, what are you going to get? 1 1 1 1 1, right? And you perform the AND operation, what are you going to get? 0 0 0 1 0. So in the OR, you can see there are 5 set bits. In the AND, there are 1 set bits. 5 plus 1 is equal to 6. Okay, and if you see both the numbers, number 1, number 2, number 1 has 3 set bits, number 2 has 3 set bits. 3 plus 3 is also equal to 6, right? So what we can do now, now the problem has become very simpler. You have to just count the number of set bits in each of the numbers, and you have to see if the sum of the set bits of any two numbers is greater than equal to k. This is the simple problem. Okay, now let's take our very own example. Let's come back to our example and let's see if we can solve this problem. Let me just copy this below, and then we'll see what is the time complexity of our solution, right? So let me just paste it here. Okay, so we have this as our array. So let's start. So basically what we are left to find is just the number of set bits in each of this, right? So you can just create an array, and you can just store the number of set bits in this array corresponding to each of the numbers. For example, 5 is 101, so it has 2 set bits. 1 is simply 1 in binary, also it has 1 set bit. 3 is 11, so it has 2 set bits. 6 is 110, so it has 2 set bits. 5 is 101, it has 2 set bits. 3 is 11, so it has 2 set bits, right? So now first of all, there's one thing you have to consider. In this question, you only have to return the distinct number of such pairs. For example, take the pair 5 6, it is occurring in the array, right? Now I cannot take another pair 5 6 just because I have a duplicate 5, right? Just because I have a duplicate 5, I may think that I can take this 5 6, but this is not a new pair, right? This is not a new pair. So if 5 6 is occurring, that means that you should take it only once, even if you have multiple 5s or multiple 6, right? So because of this, what we can do is first we can remove the duplicate entry. So you can see that 5 is repeating here. So what I can do, I can just remove this. 3 is occurring, so I can just remove this because I need only distinct pairs, right? So I can remove these last 2 outputs. Okay, let's just remove them. So now we have set bits corresponding to only unique elements in the array. Okay, now you have to just count the number of pairs which are having the total number of bits, summation of bits greater than equal to k. Okay, let's take one example. Let's say you have this 2. This 2 plus 2 is giving you 4, right? The sum of these 2 is going to give you 4. 4 is greater than equal to k, which is 4. So this is an excellent pair, right? So 5 and 3 will form an excellent pair. But just take this example. Let's say you take the example of 1 and 2. 1 and 2 is going to give you 1 plus 2 is going to be 3. 3 is less than 4, right? So this is not an excellent pair, and so on, right? So how can we find? Now the problem is reduced to another simple problem. Sum of two numbers, right? Sum of two numbers in an array should be greater than equal to k, right? That's what we are basically looking to find. So what if, how do we do that? Now it's very simple. You can just sort this array and use the 2-pointer technique to solve this problem. Let's take this example. So we have the sum of set bits, right, as this array. So I will just sort this array quickly. So you have 1 2 2 2. Okay, you have to find out sum of two numbers in this array which is greater than equal to k. Okay, what is our k? Our k is equal to 4 in our example. So let's start. So you can simply use 2 pointers to find it, right? Let's say I use the first pointer here and the end pointer here. So after sorting this array, you can easily use the 2-pointer technique. So let's see the example. 1 plus 2. Let's see what is 1 plus 2. 1 plus 2 is 3. 3 is less than 4, right? I have 2 pointers, start pointer and end pointer. Corresponding to them, I have added the numbers, I have got 3. Now 3 is less than 4. I want to get a value which is greater than equal to 4, right? So because 3 is less than 4, I will move my start pointer. Because this array is sorted, if I move my start pointer to the right side, I will get the sum to be obviously greater than the previous sum which I considered, right? That's why I will move my start pointer. So I will move my start pointer. When I move my start pointer, I see a 2. What is 2 plus 2? Let me erase the previous sum. Let me write the current sum now. 2 plus 2 is equal to 4. Now you can see that 4 is greater than equal to 4, right? So we have got one excellent pair. Okay. Now you need not even check other excellent pair. Within this range, all pairs will be excellent, because if 2 plus 2, if these two numbers are going to give you an excellent pair at least, then all the numbers which are on the right side of this start, right? For example, this 2 and this 2 will also give you an excellent pair, because whenever you move to the right side, you will obviously only get a sum greater than the current sum. Okay, so because of this, if you know that you have got this pair, the other pairs which are within the range of start to end will also be excellent pairs. Okay, so how many total such pairs will be there? So let me first of all write the indices of the array. I am just writing the indices 0, 1, 2, 3. Now corresponding to this start and this end, I have got 2 plus 2 equal to 4, which is an excellent pair, which is satisfying my condition. So what are the total number of pairs within this range? So you can see that first pair will be this 2, 2, the second pair will be this 2 and this 2, right? So there will be total 2 pairs. How you can get that? You can just do end minus start, right? 3 minus 1 will be equal to 2. You will get 2 pairs in between start and end, which are going to satisfy the condition and be excellent pairs. Okay, so once you have got this, what you are going to do, once you have got a sufficient excellent pair, you need not iterate by moving start pointer further. Rather, we can fix the, earlier we had fixed the end pointer, right, and we were only moving the start pointer. Now we can shift our end pointer and we can see if we will get better pairs, right? So I will move my end pointer after this. So my start pointer is at 2, my end pointer is at 2. Now I will check again. You can see that this 2 plus 2 is also 4. 4 is greater than equal to 4. In this, there is only going to be one pair. So answer I can increase by 1. 2 plus 1 will be equal to 3, and I will get totally 3 excellent pairs. After this, when I move my end pointer, I will see that start and end pointer are equal. If start and end pointers are equal, that means I can exit, because I need two different numbers, right? So now let's move forward to coding this. So the problem is very simple. First, we have to iterate over the nums vector. So let me start. For int I equal to 0, I less than nums dot size, I plus plus, and we have to basically count the number of bits that are set in each of the numbers, right? So we can just count the number of set bits in nums of I. So I can declare a function that is going to count the set bits in nums of I, and I can store this. First of all, I have to actually take distinct numbers, right? I have to take only distinct numbers. I need not take repeated numbers, right? So first of all, I can store all the numbers in a set so that we get only distinct numbers. As we discussed in the logic, we need only distinct such pairs, right? So I can take a set. Let me take a set, and in this set I can just directly take my nums vector and I can put all the elements from the nums vector in this set. So because of this, what will happen, our set, which is consisting of only unique elements, set consists of only unique elements. Let me take an example. Let's take this example, 5 1 3 6 5 3, right? Let's say our nums vector is 5 1 3 6. Let's take this example, 5 3, right? So this was our nums vector. So what we can do after this line, our set, which is unordered set, okay, int, let me give it a name. Let me just call it S for short, right? So after this, S will become equal to only unique elements. So it will consist of only 5 1 3 and 6. Okay, now what I can do is I can count the number of set bits in each of this, right? So I can iterate over the set. So let me start. For auto, it is equal to s dot begin, it not equal to s dot end, it plus plus. I am basically just iterating over the elements of the set. Now I can take a count set bits function and I can call that function to find out how many bits are set in any given number, right? So it's very simple. Let me take a count set bits function, and it whatever number is given as the input to it, it will count the number of set bits in that number and return that as the answer, right? So let's write this function. So there are many ways to do this, so let's just do it using the simple way. We can just check whether the last bit is 1 or not. Okay, so for example, I have to let me take one example. Let's say the number that I have is 5. I have to count how many bits in this are set, right? So what is the binary representation of 5? It is 101, right? So while number, okay, so what I'm going to do, I'm going to check whether the last bit is 1 or not, right? So how can I check? I can just take number mod 2. So I can see that number mod 2, if it is a even number, it will be 0. If it is a odd number, because of the last bit, it will be 1, right? So I can just count whether the last bit is set or not by just doing number mod 2, right? So after this, I can just remove the last bit. I can just divide the number by 2 and I can just count. So what will happen? First time it will count this bit. Because of this bit, count will become equal to 1. Okay, then I do number by 2. This bit will go off. I see this bit is 0. It will not count here. Then I will see this bit. This bit is 1. So I will add 1 plus 1. So count will become equal to 2. And then I will erase this bit also. So finally the number will become 0, right? And then I can just return count. Okay, so this will count the number of set bits in any given number, and the time complexity of this operation will be log of number, right? Okay, so this is done. Now once I have this, I can just store it in a vector, okay, and I can then sort the vector, right? So let me store it in a vector which stores, let me write the vector as stores the number of bits that are set. Okay, stores number of set bits. Okay, in fact I need not even use stores. Let's not complicate. So the name can be simple. Let's say the vector is called number of set bits. Okay, so this vector is going to have the number of set bits. Now in this vector, I can just push back whatever answer I am receiving corresponding to each of the numbers in my set. Okay, so this is done. So after this operation is performed, after this operation is done, my vector, which is number of set bits, let me write the output here. My vector should have what numbers it should have? It should have these numbers 1, 2, 2, 2, as discussed in the code logic, right? It should have these numbers. Okay, now I have to check sum of how many numbers in this, sum of how many pairs in this is greater than equal to k. That is my quotient, right? Now this is my quotient. So what I can do, I can just take two pointers. One pointer is going to start at the initial value, one pointer is going to start at the end value, right? As discussed in the logic, the question is very simple. Now you have to just see which two numbers are going to give a sum greater than equal to k, and you have to count how many such numbers are there. Okay, so while start is less than end, I can just check if number of set bits at where my start is pointing plus the value at my end pointer, if that is going to give me a value which is greater than equal to k. If this is true, that means, okay, if this is true, let me take an answer variable. By the way, it is a long, so let me declare the variable as a long. So if this is true, then what I can do, I can just count how many such pairs are there, all the pairs, right? All the pairs within the range, all the pairs within the range of start to end, right? Within this range will satisfy this condition, because if the number at the start pointer and the end pointer are satisfying the condition, any numbers in between will also satisfy the condition. Okay, so let's take some example. Let's say you have 1, 3, 5, 7, right? Let's say my start is pointing at 1 and my end is pointing at 7, right? So then in this case, the sum of the numbers, okay, sum is going to be 8, right? If my start, let me write here, just taking one example, if my start is at 1 and if my end pointer is at 7, right? So the sum of the numbers is 1 plus 7, which is equal to 8. Now let's say if I anytime increase my start pointer, right, always I am going to get a sum which is going to be greater than the current sum 8, right? So you see the next sum 3 plus 7, 3 plus 7 is going to be 10. See the next sum 5 plus 7, 5 plus 7 is going to be 12, because this array is sorted, right? Now because of this we have to sort this array. So number of set bits, first of all we have to sort this array so that we can just apply the 2 pointers technique easily to solve this problem. So I am going to sort this array. So sort number of set bits dot begin, and I'm going to sort the entire array, so I need to give number of set bits dot begin to number of set bits dot end, right? Okay, so after this array is sorted, let's say this is the array. Okay, actually this is the array, but I'm just taking another example to just explain, right? So whenever we have a start and the end pointer, if they satisfy a given condition, right, then any numbers on the right side are also going to be greater than equal to k, because it's a sorted array. Okay, so we understood this. So if this condition is satisfied, so how many such numbers we are going to get? We are going to get the numbers as end minus start. Okay, end minus start. Okay, that's it. Now after this is done, you can just decrease the end pointer to try to find further such numbers, right? So to try to find other such numbers, you can decrease the end pointer. If this number is not satisfied, you have to try to increase your sum. So you can do that by moving the start pointer, right? If you move the start pointer, you will get a greater sum. You can try to see if it is satisfying the condition. Okay, so this is done. This is the entire problem, but there is just one more catch in this. Okay, and what is that is you have 1 3 and 3 1. So they are considering the numbers 2 times, right? They are considering 1 3 and 3 1 as different pairs. Okay, so the pair 1 3 and 3 1 are different. So what you can do, you can just return first of all here whenever you are counting answer, you can just multiply it by 2, right? And then you can return answer, because they are considering the same pair 2 times. 1 3 and 3 1 are considered different pairs in this example, so you can just multiply the answer by 2 and then you can return answer. Now there is just one more thing in this. Let's consider when you have the same number, for example 3 3, they are considering 3 3 also as one of the pairs, right? Even though 3 is occurring only once in the nums array, you are considering 3 3 as a pair. So because of such cases, even when you have a number, right, so what you can do, you can just check here, right? Whenever you are checking the count, okay, let me take one example. So you have the number 3, you have the 3 occurring only once in the array, but what they are doing, you take the number of set bits in 3, the number of set bits in 3 is 1, because it's 2, because what is the binary representation of 3? The binary representation of 3 is 1 1, right? So the number of set bits in 3 is equal to 2. Similarly, the number of set bits in 3 is equal to 2. Now let's say 2 plus 2 is equal to 4, right? Let's say 4 is greater than equal to k. So in this example, you can see that 3 3 is also a valid pair. So where should we include it? So what we can do, when we are counting the number of set bits here, right, so you can just check if 2 into count, because what we are counting the number of set bits in a number, right? So when we are using that function to count the number of set bits, we are getting our count as 2. So you can check if 2 into 2, right, which is equal to 4, if that is greater than equal to k or not. So we can just check if 2 into count is greater than equal to k, then you can just add this in the answer. So for this I will have to pass my answer and I will have to pass k in the input parameters of this function. So let me just do that quickly. So let me just take this function which is count set bits. So in this function I can pass answer and I can also pass k. So let me declare this answer before here. Okay, so that's it. Now let's run and see whether this code is going to work or not. So it's working. Let me submit and see if it's going to work for all the test cases. So, and the time complexity of this is n log n, because we are going to sort this, and the space complexity is order of n because we are using a set. Thank you.